Next, I want to cover groundwater, or the water subsurface or underground water. So we covered surface water here, and now we're covering the water that's below the ground, which is incredibly important because groundwater is the second largest source of fresh water on Earth after glacial ice, and it is incredibly important as a water supply in California. So let's look at the mechanics of it. Groundwater is stored underneath the ground, and it's stored in a structure called an aquifer. An aquifer are sediments and rock underground that water can flow through and water can be stored in. So you have impermeable rock below here. You have certain types of rock and sediments here that can store water. Sometimes you can have an intermediate layer that blocks water called an aquiclude, and then perhaps even another aquifer above that aquiclude. This is a figure showing some principal aquifers in the western United States. The most important one in California is the Great Central Valley Aquifer, shown here. Then there's a number of smaller aquifers along the coast and shallower aquifers in the interior. If you look at from the side, an aquifer is going to have different zones. It has an unsaturated zone. That's the land, that's the area above the water. Then you have the saturated zone below, and that's actually where the water is stored. And what divides them is a water table. The water table is the surface of the groundwater, or the surface of the saturated zone. And what we're interested in is what affects where that water table is, because the water table sometimes will be lower, and then sometimes will be higher. Also, I should point out that the aquifer is made up of sediments or fractured rock. So the water, think of the aquifer as sort of a sponge. A sponge is a solid object, yet can store water within it. So if we want to look at how the water table changes over time, we have to look at how water goes in and comes out of these aquifers. So water comes in through recharge. Recharge happens through precipitation or from rivers soaking into the ground. And you can also have artificial recharge. And this is where surface water is diverted through canals and put in areas that are where the water can easily permeate into the ground. For example, this is a picture of Leaky Acres, an area near 168 in Ashland and Fresno, where they have a number of these large ponds that can be filled up from canal water and then allow water to be soaked into the ground. One thing to note about natural recharge is that there's much less recharge in the southern part of the Central Valley than there is in the north. The north is much wetter and also has rivers with a larger amount of water in them. The south is a drier area and has smaller rivers. So recharge can vary by where you live depending on how much rain you get and how much water comes in from rivers. So you have, in this image here, you have some recharge happening because of rainfall. And you also have artificial recharge basins that are used to help to support the level of the water table. Now, one major issue in places like California is water mining. Also, we call it overdrafting the aquifer. And this is when you pump out groundwater at a rate at which it can't be replaced. And so, water has filled up in these aquifers over long periods of time. And we are, in some cases, removing that water much faster than it can be naturally replaced. One side effect of this has been subsidence. One thing about water mining. So there's a twofold problem in places like the Central Valley, that under natural conditions, not only were we not pumping water out, but we were also not using the natural water as much. So fresh water would come in from rivers from the Sierra Nevada. Much of that water would soak into the ground and help support the water table of the aquifer. However, what's happening now is that we're doing two things. One, we're diverting the surface water and using it for human consumption, including agriculture and urban use. And two, we are pumping water out of the aquifer. So by limiting the inputs and increasing the outputs, we are lowering the water table in places like the Central Valley. One side effect of this is subsidence. And subsidence is when, through excessive pumping of water, you have a general lowering of the ground level. So here's an image showing subsidence in the western San Joaquin Valley. This was a big problem from the 1920s up to the 1970s before new canal infrastructure brought more water to reduce the amount of pumping that was happening in areas from Mendota down to Huron. This is a famous image from a report that was done in the 1980s showing the level of subsidence from 1925 to 1977. This is a guy named Robert Poland who studied subsidence in the Central Valley. And he made this interesting graphic where he put a label on a telephone pole that represents where the ground level would have been in 1925. And by 1955, it had subsided or sunk down to this level. And by 1977, it had subsided to that level. So there's been a massive lowering of the land. That's at its worst here in areas on the western part of the San Joaquin Valley. And we've had, during the previous drought, we've had more recent subsidence because of the excessive amount of groundwater pumping. This is Michelle Sneed, who has the job of Mr. Poland that used to have. She's the current person who studies this in the Central Valley. And she has a similar graphic showing changes between 1965 and 2016 for one of these areas, not so much on the west side, but more in the middle of the valley, where we've had a lot more almond and pistachio crops that require a lot of groundwater pumping during the drought.